Hello everyone, my name is Alireza Jafari. I am a PhD candidate in civil engineering at Dalhousie University with the supervision of Dr. Pedram Sadeqian. And today I am presenting part of our research entitled Developing Eco-Friendly Concrete with Sustainable Supply, the Potential of Using Whole Recycled Gypsum Drywall. So first I start with the outlines. So for the presentation, I will start with introduction. So in the introduction, we say why replace cement is important, why new supplementary cementitious materials, why recycled gypsum drywall, and why we are interested in reusing whole recycled gypsum drywall. Then we go for objectives, test matrix, test results. In the results, I will explain the result for feasibility of whole recycled gypsum drywall, and then we go to conclusion, and then I explain you briefly the in-progress research that we have on the short-term properties and long-term properties of the concrete. So why do we need to replace cement? We all know that cement has environmental impacts. So for the environmental impacts, we can categorize it into two sections. The first one is about the natural resources, because we know for producing the cement, we need natural resources. Approximately for each tons of cement, we need 1.5 tons of raw materials, and this could result in resource depletion and put a significant strain on the planet. On the other side, when we go to climate change and carbon dioxide emission, we know that producing cement, not only the production stage, but also the storage and transportation and reaction phases all would emit the carbon dioxide, and that would result in the contribution of almost 8% to the annual carbon dioxide emission globally. So based on this, we can see because currently the cement is the primary binder of the concrete with over 4 billion tons supply per year. So using this amount of cement could emit 3.28 billion tons of carbon dioxide emissions. And based on our estimations, almost cement is responsible for almost 86% of carbon dioxide emissions of the concrete. So what's the best approach to reduce that carbon dioxide emission? The best approach is to replace cement, ordinary Portland cement, with eco-friendly alternatives. So why do we need new supplementary cementitious materials? The primary reasons are these 5 reasons. First of all, we don't have that much available SCMs that we can use to replace cement by the research that we have. So we have fly ash, slag, silica fume, and so on, but the amount that we have is not enough to what required to replace ordinary Portland cement. On the other side, we have new environmental regulations that start to restrict and limit the amount of SCMs that we have. For example, we have new regulations that begin to ban the burning of coal in the power plants, and for these ones, when they applied, then we will have limitations in fly ash, which is the primary SCM right now. Besides these impacts, we know that we need to reduce cement to reduce the carbon dioxide emission of the cementitious composites, because we know concrete is the second most common material that we use, and beside these environmental impacts, which regard to SCMs and also cement, on the other side, when we look at the use of reusing waste materials, we know that by reusing them, we can offer a sustainable waste management practice for the potential materials, and also use their feature to improve the strengthening reaction of the system. So why we are going with recycled gypsum drywall? The primary reason is the abundancy of the material, because we know that the gypsum drywall usage is increased because of its potential in sound and heat isolation. So right now, it's accounts for almost 20% of construction and demolition waste, From environmental perspective, we know that if we reuse them, if we reuse gypsum drywall, we prevent landfilling these hazardous material, and by doing so, we don't have toxic gas and water and soil contamination that would result from landfilling gypsum drywall. And we can also offer waste management practice for the gypsum drywall. When we go to economy, we know that by recycling materials, we can promote circular economy. So we have cheaper cementitious materials, and the most important thing here that attracts our attention is the closed recycling loop of the gypsum. So we can recycle gypsum as many times as we want, and it comes back to its original reactivity. So based on these, we go to use recycled gypsum drywall and find what we have in the literature. So in the literature, typically researchers use the fine recycled gypsum drywall to have a compatible particle size with the cement. They find that the gypsum drywall, recycled gypsum drywall, can activate fly ash and slag, can reduce the cumulative hydration heat by up to 73%, which is significant for large projects. It can produce dense ettringite crystals, so it typically changes the thin needle to thick needle ettringite and provide a frame structure which can carry load, and it can also improve some of the durability characteristics, including the resistance to alkali-silica reactions. However, it increased the porosity of the system because of the fibers that we have, and we will explain it in the next slide. So what's the problem with using fine recycled gypsum drywall? The primary issue is that only 30 to 45% of the RGD would pass sieve number 50 and have a compatible particle size with the cementitious materials. So by just using fine recycled gypsum drywall, we almost return between 70% to 55% of recycled gypsum drywall to the landfill, which could result in the landfilling issues and environmental impacts that we already discussed. And we know that because of the recycling loop, so the RGD has a potential to be used as SCM and fine aggregates in the concrete. We use both, but in this presentation, I just go with the SCM. So based on that, the primary focus of this study is assessing the potential of whole recycled gypsum as a binder, either cement or fly ash alternative in high volume fly ash concrete, and compare the result with the fine recycled gypsum drywall. I also go to briefly explain our in-progress research on the short-term and long-term performance if I have time. So the primary objective, as I mentioned, is evaluating the feasibility of using whole recycled gypsum drywall instead of fine recycled gypsum drywall as an SCM in a concrete, and we examine mechanical strengths, ultrasonic pulse velocity, microstructure, and bulk density of the system. So here you can see the mixed design. In the mixed design, here we have fly ash, which represented by F. WG represents whole gypsum, and FG represents fine gypsum. So you can see by having this mixed design, we can evaluate the effect of whole recycled gypsum drywall and fine recycled gypsum drywall as both cement alternative and fly ash alternatives. And here you can see the SEM pictures of the fly ash and recycled gypsum drywall and their chemical compositions. So for the test, as I mentioned in the objectives, we go for bulk density, ultrasonic pulse velocity, compressive strengths, and microstructure. We test the specimen at 7, 28, and 90 days, and we use the moist curing regime. As you can see here, we have a moist curing room and put the specimens in there till the testing day arrive. So for the results, you can see that when we use recycled gypsum drywall, either as whole and fine particles, we receive almost the same results, So here, if you compare the green one with the blue ones, we almost received the same results, which show us the potential for whole recycled gypsum drywall instead of fine recycled gypsum drywall. We almost show that if we replace cement with recycled gypsum drywall, then the strength dropped. However, if we replace fly ash with the recycled gypsum drywall, the strength does not significantly affected. It just decreased between less than 10% at 90 days. But the main issue right now is the low early age strength of the system compared to what we have for F40. So we go to examine the effect of biochar. So if you were in a biochar session, they use the powdered biochar, but we use the whole biochar because of its potential to provide water. So it acts as a water reservoir for internal hydration and can promote the early age strength of the system. It can also increase the ductility of the system. And it's important for us because by adding recycled gypsum drywall, we actually increase the brittleness of the system. So we need more ductility, which could be provided by the biochar, and we also reduce the carbon footprint of the system. So the results for this session is not presented here. They are just what we have been done. And we also test the preheating of recycled gypsum drywall and find that it could boost the early age reactions of the system. However, we do that in the mortars, not in the concrete. So the data are not here. And when we use the artificial intelligence, we find that the AL to S ratio in the fly ash and RGD could be used to optimize the dosage of recycled gypsum drywall. So when we go for bulk density and ultrasonic pulse velocity, for bulk density, we can see the use of whole recycled gypsum has more effect compared to using fine recycled gypsum drywall. And we suggest that this effect could be because of the fiber accumulations, because RGD in its original form contains some fibers, because we just use the original one, we don't do any treatment. So we expect that the fiber accumulation could result in the difference between the bulk density of mix containing whole recycled gypsum and mix containing fine recycled gypsum. However, when we go for UPV, we can see the UPV of the system is almost consistent with the F50, which show us the potential of RGD in both shapes as a replacement for fly ash. And when we go to microstructure, you can see the microstructure of the specimens containing only fly ash and specimens containing fly ash and whole RGD. So based on the SEM pictures, we can see that in the cement paste, without any RGD, the cement paste primarily composed of CSH and calcium carbonate. But when we add recycled gypsum drywall, we can see some ettringite. So we have condensed ettringite in the SEM pictures, so it promotes the formation of concentrated ettringite. We can also see some reactions on the fly ash particles that attach to the fly ash particles, and that shows the RGD can promote the reactivity of the fly ash, because in the specimen without recycled gypsum drywall, we don't have that reactions. For incorporation, we also see some micro cracks in the SEM image. We don't know exactly whether they are because of testing specimens after the compressive strength or they are originally there. So we are going to find it out. And for the fiber accumulation, you can see the fiber accumulation here. So these are the fibers that accumulated on the sieve, and this is the fiber accumulation that we saw in the SEM image. So these fiber accumulation could form weak spots in the concrete. So by treatment or refining the recycled gypsum drywall to remove the fibers, we may improve its performance. And so based on that, we go to the conclusion. So we find that whole recycled gypsum can be used in high volume fly ash, concrete as replacement for both cement and fly ash. However, ideally it can be used as a fly ash replacement. We saw that the use of recycled gypsum drywall actually reduced the early age strands. However, when we wait till 90 days, then the delayed reactions of RGD enhance the strength of the system. So we go to promote this strengthening and remove the delayed reactions and replace it with early age reactions by preheating and using biochar to provide enough water for it. We find that we need a treatment to remove the fibers because their accumulation can create weak spots in the system, and we find that RGD would promote the formation of ettringites in the system and also boost the activity of the fly ash. So for the in-progress research, we go based on the result, we find that replacing fly ash would be an optimal approach. So we go for this mix that you can see here. We have the new test matrix, and we go for evaluating short-term and long-term properties. For short-term, we just add the modulus of elasticity, but for the long-term, we have 4 different environments and test factors or dimensions: strength loss, modulus of elasticity, weight loss, UPV, and microstructure. And thanks for your attention. So here is my research areas. So we use biochar, hydrochar, flags, and recycled aggregate to promote the reactivity of the system. I also did some research on geopolymer and alkali activated concrete. For duration, we go with short-term and long-term. And for test, we go for compressive strength, porosity, which is bulk density, and UPV. And microstructure, carbon footprint, stress strain behavior, and wave propagation. And if you want to know more about our research, you can scan the QR code so we can be in contact. Thanks for your attention.